Good morning, chemistry students. We left off explaining, we talked a little about J.J. Thomson and the electron, Eugene Goldstein, and the detecting those positive particles, and James Chadwick detecting those uncharged particles. And at this point in time, we really don't understand where those particles are found. We just know that we have particles. We have particles that are positive, some that are negative, and some that contribute to mass but don't appear to be charged. But we really don't know much about the actual structure of the atom itself. But there was a groundbreaking experiment done by Ernest Rutherford in New Zealand in the early 1900s. Rutherford's gold foil experiment is really famous because it helped us detect the existence of the nucleus, which we know most of the mass of an atom is in the nucleus. So by this point in time, we do know that atoms are mostly empty space, which I know when we look at models of atoms, we don't necessarily represent them that way, but we do know that we did know that there was a lot of empty space in an atom, but we didn't know where those particles were. So he fired these tiny positively charged alpha particles at a very thin sheet of gold foil that was so thin it actually was one atom thick. So the thickness was the thickness of one atom of gold. And he expected to see these particles mostly just passing right through, with maybe a few of them showing just a slight deviation due to the alpha particles were positive, and he knew that there were positive particles in the atom. And so he expected to see those alpha particles, mostly they're very tiny, just pass through, and a few of them might be slightly defected. But what he saw was something very different and surprising. He saw that a lot of the particles showed a greater deviation than would be expected by just coming into contact with the charge. And some of them even bounced straight backwards. So if they're only being deviated by the charge, we certainly wouldn't see any of them bouncing backwards like that. And I'm going to have you watch another supplemental video, a YouTube video that kind of shows a little bit more about how he set this experiment up, so that hopefully it is more clear kind of what he did. So his conclusion is that, oh my goodness, these are not deflecting simply because of charge. They are deflecting because they must have hit something very solid. So yes, there's empty space in atoms, but he concluded there must be a solid center of atoms, which we now believe to be true. And that solid center contains, we know now, the protons and the neutrons tightly packed together. So again, groundbreaking work and very important in helping us determine that structure of the atom, which until this time was pretty largely unknown. All right, the last part then of this chapter, and I feel like chapter 1 is very short. We're going to talk about isotopes and some of the differences, how they're different from each other, and kind of what makes an isotope. So we already talked about this, the information that we find when we look at the periodic table. You should already be familiar with that. So we see the element symbol, and we see the element name, the atomic number, which is the number of protons. This is actually how we identify atoms. And then the mass number in atomic mass units is the number of protons plus the number of neutrons. But you'll see that it's not an exact even number either. So there's a reason kind of for that. And just remember, we measure these in atomic mass units because obviously these subatomic particles, protons and neutrons, are very tiny, so it would be silly to measure them in ounces or pounds or grams or something large like that. So isotopes. When we look at this number on the periodic table, this atomic mass, this is actually an average atomic mass of all of the existing isotopes for that element. And some elements, there's really only one or maybe two isotopes. With some elements, there's there's many more than that. Carbon actually has 3 different common isotopes, and some more common than others. So we look at carbon, so there's a carbon 12, there's a carbon 13, and a carbon 14. So isotopes are atoms with the same number of protons. So all atoms of carbon, for example, always have 6 protons. That's actually what makes it carbon. So all of the known isotopes of carbon have to have 6 protons because, again, that's what makes it carbon. But they can have different numbers of neutrons. And so the mass is different because of that. And the correct way to write isotopes is we can say carbon 13, which then indicates that it's the carbon atom that has a atomic mass of approximately 13 or very close to 13. When we write the symbol of isotopes, we represent the atomic mass and the atomic number. So this is carbon 13. Okay, for a quick little lesson on isotopes. So if I look at oxygen, oxygen has 3 common isotopes. There's oxygen 16, oxygen 17, and oxygen 18. If I want to know how many protons are in oxygen, I can look at the periodic table and see that oxygen has an atomic number of 8. So I know that oxygen has 8 protons, and that would be true regardless of which isotope we're talking about, okay? So if it has 8 protons, remember on the periodic table, these are neutral atoms. So 8 protons also, they would all have 8 electrons. What is going to be different are the number of neutrons. So oxygen 16 has 8 of this mass are the protons, so 16 minus 8 must mean that there are 8 neutrons. Oxygen 17, we take 17 minus 8 to get 9 neutrons. So again, the atomic mass is different, and then oxygen 18, of course, would be 10 neutrons. So there's a really cool way you can kind of figure out by looking at the periodic table which element is most abundant. So if I'm going to find the average atomic mass of all of the naturally occurring oxygens, I need to calculate a weighted average, because if I just took an average of all 3 of these, that's not really an accurate depiction, because one of them occurs like 90-some% of the time and the other ones are fairly rare by comparison. So if I want to calculate the average atomic mass, I need to calculate a weighted average. So I always say this is a little bit like what we do on Skyward, where we say, okay, I'm going to calculate a weighted average of your grade where tests are worth 50% in this class. Your lab work is worth 30%. So even if I have 1,000,000 points in labs, it's 30% of your grade. Okay, it's never going to weigh more heavily on your grade than, say, tests, which are 50%. So I'm calculating a weighted average. So here's how we do that. So that atomic mass in the periodic table is a weighted average. So let's look at if I have 2 isotopes of chlorine. There's a chlorine 35 and a chlorine 37. The exact average atomic mass of chlorine 35 is slightly less than 35. It's 34.969 atomic mass units. So super close to 35. Chlorine 37, that isotope has a mass of 36.966 atomic mass units, so just under 37. Percent abundance, the chlorine 35, 75.77% of all the chlorine on Earth is actually this isotope. So 3/4 of the time, if I just take random samples of chlorine, 3/4 of those atoms are going to be chlorine 35. The other 24.23%, so almost a quarter of them, are chlorine 37. So if I want to know the average atomic mass, I have to take into account that one is more rare than the other. So here's how I calculate that. I turn my percentages into actual numbers. So it becomes 0.7577. 24.23 becomes 0.2423. And then I just multiply these across. That's the first step. So 34.969. I'm going to pause this while I do my calculations. All right. So if I multiply this across, 34.969 times 0.7577, I get 28.011. Look at that number and say, does that make sense? Does that seem correct? And it really does, because if I had 34.969 times 1, it would be 34.969. But I'm less than 1, so 28 is about 3/4 of that number. That seems right. And 8.957 is about 1/4 of this number. That seems logical. And then for the average atomic mass, I simply add these up. So after I've multiplied those across, I really just add them up. There's no, please don't divide by 2. And because we've done a weighted average, there's not a add them all up and divide by 2 kind of thing. I think that's the biggest mistake that I see students do with this. We've already multiplied across by the percent of natural occurrence or percent abundance, and then we just add these up. So the average mass of all the chlorine, and this number doesn't match the periodic table, so I actually think I'm missing an isotope here. But if I did this, if I had all the isotopes of chlorine and I did this, it should come up to be exactly what we see in the periodic table. But like I said, it's not. So clearly, this isn't an accurate representation of chlorine. But here's what I can do with this number after I calculate this. I need to make sure, does that seem logical? If this is a weighted average between these two numbers, this number should be somewhere between these two numbers, somewhere between, okay, never mind. I found an error. I had multiplied wrong here. Actually, I'm pretty sure I multiplied right like 6 times, but I'm using my phone and it just, I don't know why it consistently gave me the wrong answer because I double checked it 4 times. But anyway, so because I knew when I looked at that number, I'm like, that doesn't make sense. This number should be somewhere in between these two numbers. And it should be closer to the one that's more abundant. That's a good check at the end. So 36.21. So this is almost 35. This is almost 37. So I'm in the middle. But it should be, remember, weighted average of these two. So somewhere in the middle, a little closer to this one. So hopefully that is a little closer to, please, if my math is wrong, please correct me tomorrow because I seriously, I think it's my phone calculator. Anyway, so that's the average atomic mass. And again, this isn't matching what's on the periodic table, so I'm sure I missed something, but that's the technique anyway. So yeah. So I think on your worksheet you have some practice with that. So I'll have you, I'll give you another worksheet to practice a little more because this is, you know, an important math that I think we should spend a little bit of time on.